Wheatstone Bridge explained in 2 minutes. The Wheatstone Bridge is used in a number of applications, but perhaps the most famous one is resistance measurement. We have 4 resistors connected as shown. R3 is a variable resistor, and Rx is the resistor whose resistance is to be measured. This is a galvanometer. You can think of it as an ammeter that is extra sensitive and can therefore measure current in the microamp range. The idea of the Wheatstone bridge is to vary the resistance of R3 until the current in the galvanometer is 0. At this point, we say the bridge is balanced. Okay, so how does this help us determine Rx? Before we head into the circuit analysis, I want you to remember that although we typically draw the Wheatstone bridge like this, it doesn't have to be drawn diagonally. So if you see a circuit like this one, for example, then this is of course a Wheatstone bridge as well. As long as it's electrically equivalent, the way you geometrically represent a circuit doesn't really matter, except for aesthetics perhaps. So, since Ig is 0 in a balanced bridge, I1 must be equal to I3, and I2 must be equal to Ix. Also, since Ig is 0, there is no potential drop across the galvanometer, so nodes A and B are at the same potential, meaning the voltage across R1 is equal to that across R2, and the same can be said about R3 and Rx. Let's divide those two equations by each other and flip them over to solve for Rx. I1 is equal to I3, and I2 is equal to Ix. So we get this equation relating the 4 resistors, allowing us to solve for Rx. This becomes R2 times R3 over R1. Usually, we like to represent it as R2 over R1 times R3 because this tells us that Rx is equal to the ratio of the 2 fixed resistors multiplied by the variable resistor. Finally, the Wheatstone bridge is precise in measuring resistances in the mid-range, say 1 ohm to 1 mega ohm. If you have a smaller resistance, you would need a milliohm meter to measure it. And if it's higher, then you better use a megger.